Okay. So similar to power cycle, here we have Carnot cycle, and it's called reversed Carnot cycle. Okay. So if you remember when we talked about Carnot cycle in power cycles, we said Carnot cycle is a complete reversible cycle, consists of 4 steps, 2 of them reversible isothermal, 2 of them isentropic. Carnot cycle has the maximum theoretical efficiency. No power cycle can achieve the thermal efficiency that you can obtain by Carnot cycle. And this is the same here we have. If you have Carnot cycle that operate at a heat pump and you reverse everything in this cycle by reversing the direction, and then you can reverse like the heat transfer direction from low to high temperature. So in this case, if you reverse Carnot cycle, you will have something called Carnot refrigerator or Carnot heat pump. So you have Carnot as power cycle. If you reverse it, then you will have Carnot refrigerator or you have Carnot heat pump. And again, the reversed Carnot cycle or Carnot refrigerator or Carnot heat pump, it has the most efficient refrigeration cycle. So again, this is your benchmark cycle. If you have refrigeration cycle, heat pump cycle, and you want to see what is the maximum theoretical efficiency, so this will be based on the reversed Carnot cycle. Okay, so similar to what we did in power cycle, this will be the same here. So if we see Carnot cycle, so again, these are the components of Carnot cycle. Again, compressor, similar to the power cycle, turbine, similar to the power cycle, condenser, boiler or evaporator, similar to what we have in power cycle. But what are the differences? That everything is flipped. So what this means, that you have the fluid will go from the turbine, it will go to the boiler. After the boiler, it will go to the compressor. After the compressor, it will go to the condenser, and then it will go to the turbine and continue the cycle. And this direction is reversed. This was the reverse of what we have in power cycle. Power cycle, we have the boiler or the evaporator, then go to the turbine, then the condenser, then the compressor. But here we are flipping it. So this is number one. Number two, we have the evaporator or the boiler operating at low temperature. We have the condenser operating at high temperature. Okay. So if we did this and we need to see the TS diagram is almost the same. Okay, we have TS diagram, we have one path or two paths isothermal, two paths isentropic, but if you see the arrow here, so the arrow direction is reversed. So previously in power cycle, this is what we have. We are moving in this way. This is the direction of power cycle. So this is the power cycle direction. But here in the refrigerator or heat pump, so we just reverse it. Okay? And again, we still have process 2.3 and 2.4, this is isentropic. Process 4.3 and process 2.1, this is 2 isothermal. Again, Carnot cycle or reversed Carnot cycle, this is still ideal, but it's still theoretical. It's not practical. Why? Because we still here have point number 2 and point number 1. So these 2 points having mixture of liquid and vapor. So we have liquid vapor mixture. And then we don't have any compressor that can handle 2 phases. We don't have turbine that also can handle or make expansion of high moisture content refrigerant. Okay. In the power cycles, the fluids that is moving in the cycle is called working fluid. Here in the refrigerators or these cycles, it's called the refrigerant. So this is the name of our working fluid. So almost everything is almost the same, but it's reversed. So if you understand the power cycle, just reverse everything, reverse the direction, reverse the arrangement of the component, then you will have a heat pump or refrigeration cycle. Coefficient of performance of a Carnot cycle, we said the general equation to obtain the coefficient of performance. So the equation that we obtained in the previous slide, these were the generic ones that you can use for any cycle. But again, Carnot cycles, we have another equation, extra equation we can use that is based on only the temperature. So if you have Carnot cycle operates as a refrigerant, so this will be the equation, 1 divided by higher temperature over lower temperature minus 1. If you have Carnot cycle operates as a heat pump, so the coefficient of performance of it 1 over 1 minus TL over TH. And how I can increase the coefficient of performance of Carnot cycle, either refrigerator or heat pump. So basically, you can increase the coefficient of performance if the difference between the temperatures decrease. So if you have delta L decrease, then this means the coefficient of performance will increase. And how you can minimize or reduce the temperature difference, so with the TL, the low temperature, you can increase it, or the high temperature of the condenser, you can decrease it. So and the coefficient of performance of Carnot cycle only depend on the temperature. It doesn't depend on the type of the working fluid. It doesn't depend on the pressure you have in the system. It doesn't depend on the phase, only what is the boiler temperature, what is the condenser temperature. If these temperatures are getting close to each other, then the efficiency will be high. If the difference between these temperatures getting large, so the temperature or the efficiency or coefficient of performance will be decreased. Clear?